G is the genus, and B is the number of boundary components. And we're only looking at things with negative Euler characteristic. So we saw that the space of hyperbolic metrics and markings, Teichmuller space, is homeomorphic to 6G minus 6 plus 3B. Okay, so that's and the way the proof went is we looked at Pan's decomposition, so we could cut up our topological surface into pairs of Pans. And then these parameters were things that determine these pairs of Pans, these lengths and determine the gluing, right? The twist parameters. So there's one more sort of geometric fact that I wanted to tell you to complete the picture. So now we have these hyperbolic surfaces built out of these pairs of Pans. There's one more geometric fact is what is called the color lemma. So that's the following. So if you have a hyperbolic surface, then so the sort of the informal way of saying it is that short geodesics have large collars. Short geodesics on X have large collars. And so we already see this on a pair of Pans. So if you take a pair of Pans where, let's say, two boundary components are these, and there's one boundary component which is very short. Okay, so then it turns out that a hyperbolic pair of Pans would look like this and would have this short boundary would have a large collar. It would have a large embedded annulus around it. And this can be quantified. So there's something called, which you can call a collar function, eta of L. It has this expression. So it increases as L decreases. This is geometrically, this measures the distance between, suppose you have a geodesic segment hyperbolic plane of length L. You drop these perpendiculars, these perpendicular geodesics, and look at this infinite geodesic, then eta L is the distance between this geodesic segment and this geodesic line. Okay, so sort of if you plot the graph, eta L with L, it's as I said, it kind of increases as sort of qualitatively. That's the picture. So the more precise form of the color lemma is that if gamma is a simple closed curve as a geodesic that of length L, okay, so then an eta L neighborhood of gamma, which is all the set of points on X, such that the distance in this hyperbolic metric on the surface from gamma is less than eta of L. So this neighborhood is an embedded annulus, is an embedded collar. Okay, so that's the color lemma. And moreover, I'm not writing it, so disjoint geodesics, simple closed geodesics like this, would have disjoint collars. Okay, so somehow the picture of the hyperbolic surface would be something like this. So maybe there's a hyperbolic surface, maybe there's a very short curve somewhere and somewhere else. I mean, so somehow these short curves would have these large collars around them, and so anything disjoint would have some disjoint collars of this size, eta L. Here's another short curve, maybe it has color like this, and so on. So that's what a hyperbolic surface would look like. And one consequence of this is if you have a short curve, let's say gamma is very short, then any other curve that intersects it would have to pass through this annulus. So any other curve that intersects it essentially, okay, would have to pass through this annulus, so that will pick up length. So, so one corollary of this color lemma is something which is a special case of what is known as the Margules lemma. It says that there exists a constant L naught, in fact, independent of x. Okay, so this doesn't depend on what hyperbolic surface you're looking at. On the hyperbolic matter, only on the topology of the surface, such that if gamma 1 and gamma 2 are two geodesics of length less than L naught, okay, so then, and suppose, and one of them has, is at least is simple, okay, so then the picture looks like this, then they can't intersect each other. Okay? If both are short, then you can't intersect, so then they are disjoint. Or equal, of course, but they can be, could have picked the same curve in class. Okay, so so that's one consequence of the color lemma, which we will use in the course of this lecture, next lecture. But that's also belongs to this geometric picture. And the proof of this color lemma is again some exercise in hyperbolic geometry. One has to analyze a pair of pans, and you have a picture in the upper half plane, and somehow this is sort of the, so here the color is all this region sort of on this side. So this is somewhat the sort of the worst case scenario. Okay, so you have to sort of analyze the picture, what happens on a pair of pans in the hyperbolic plane, and it's not too hard. Okay, so all right. So okay, so this is one geometric fact that I wanted to let you know. So today we'll sort of switch our perspective and look at things from the algebraic viewpoint. So so we'll relate all this what we've learned with surface group representations into PSL2R. So we're going to look at the space of representations of the fundamental group of the surface into PSL2R. It's not a surprise that PSL2R appears. That's the isometry group of H2. And what is this? Is a space of all the homomorphisms from pi1s to PSL2R up to conjugation. Okay, so these are representations or homomorphisms. And what does the equivalence mean? So rho 1 is equivalent to rho 2 if and only if they're conjugates of each other. Okay, so where A is some matrix in SL2R, and for every so every element of pi1 of S, the image matrix is a conjugate by that same. Okay, so so that's a space. So let me say what they are in some special cases. If S is so S is a surface with boundary. So in our notation we had G and B, so B is greater than 0. So then what's the fundamental group of that SGB? So that's just going to be a free group, and it will have, you can convince yourself, is 2G plus B minus 1 generators. Okay? And so what is this space of representations then? Well, so each of these generators, you want to have an image which is a matrix. Okay, so something in PSL2R, and there are no relations that need to be satisfied. It's a free group. So you just need a bunch of these matrices. So in this case, the representation space becomes is equal to, well, you need one matrix in PSL2R for each of these generators, and then you have this quotient by this conjugation action. Okay, so you conjugate each factor. these matrices here. So that is so what this space looks like when S has boundary, and if S is closed, the closed surface, just genus G and no boundary, then you know what the fundamental group of such a thing is. And so here the representation space sits inside. Now you have one matrix for each of the 2G generators, the usual ones. Okay, and it sits inside this space. And you also need that these image matrices of each of these generators satisfy that relation. Okay, so this is cut out by this one equation that you get by you cut out by some equations you get by coming from the relation that needs to be satisfied for this to be a homomorphism. Okay, so you get what is, you can say, is a real algebraic variety. So here is PSL2R. You're looking at real numbers, and so this is. So I'll sometimes refer to this space of representations as the representation variety. Okay. Okay. So the goal today, is to see. So we'll see that Teichmuller space that we saw last time sits inside this representation variety as an open set. Okay, and also this open set comprises of some subset called discrete faithful representations. So we'll also see that if S is closed, so this Teichmuller space is in fact sort of equal to some subset of this representation space called, which have all the representations. Well, so it has all these representations here are discrete and faithful representations, and they form. In fact, if I have time, I'll tell you how they form a component of the representation variety. Okay, so it turns out that this, for if S is closed, then this space is actually not connected. It might have different components, and this, in fact, Teichmuller space equals one of them. Okay, and these are exactly these are the ones that contain these discrete faithful representations. Even here, when they in general, it lands inside discrete faithful representations. So what is discrete and faithful? So let me now, so that's the goal. So let me say a bit about discrete faithful representations now. So by the way, one can sort of do a quick reality check to check that, it indeed makes sense. So, for example, here the dimensions should match if they're sort of sitting inside this Teichmuller space. You already know the dimension, 6G minus 6 plus 3B, sitting as an open subset here. So what's the dimension of this space? Well, if you look at this, so PSL2 are these matrices which have 3 independent parameters, right? So this has the number of parameters. Let's sort of just do a heuristic count. Is 3 times 2G plus B minus 1. Okay, you have these many things. And then you're quotienting by conjugation, which subtracts 3, because there's, again, another 3. And that is 6G minus 6 plus 3B. So that's sort of the, and you can do a similar calculation here. Indeed, it makes sense. All right, so what is a discrete and faithful representation? So if you look at pi 1, a representation or a homomorphism, it's just a representation, is just a homomorphism. So is called discrete if its image, which is some group gamma, we'll always call this image of this representation gamma, is a discrete subgroup of PSL2R. Of course, this PSL2R has its own topology. It's just a set of matrices, after all, and any subgroup is discrete if the identity element has a neighborhood with no elements of gamma, right? So it's discrete in that induced topology. Okay, so that's what it means for representation to be discrete, and it's called faithful if rho is injective. Okay, this is just another way of saying that this representation is injective, and what it means then is that this would be, and the image group would be isomorphic to pi 1 of s. Okay, so you have a surface group, a fundamental group of a surface sitting inside PSL2R. Okay, something abstractly isomorphic. Okay, so that's discrete and faithful. And why do we care about discrete and faithful? So recall that PSL2R acts on H2 by isometries. You all know the action. So if you take a matrix, A, B, C, D, and you take a point in H2, you get this linear fractional transformation. Right? So that's the action. And the lemma, or the fact, let's say, is that if gamma, a subgroup of PSL2R is discrete, so you start with discrete subgroup. Of course, it also acts on H2, and well, if it is discrete, then this action is nice. Okay, so then gamma acts properly discontinuously on H2. Okay, and you already know what proper discontinuous means. A proper discontinuous action means that if you take, so here's our H2. If you take any compact set, K, it's a compact set in H2, then this group acts here and it moves this compact set various places, but there are only going to be finitely many elements, so that which moves the compact set onto itself or kind of overlapping with itself. Okay, so most of the elements would move the compact set away, and this is needed to make this for this action to be nice and to spread out. Okay, so if you look at all the elements, so that gamma, if you push K with gamma, it intersects K, then the number of this is finite. Okay, so this is one sort of definition of properly discontinuous. Okay, so in particular, what happens is you don't have orbits of a point accumulating, right? So you can't have infinitely many of these elements. So this, this is something. So a discrete group acting on a space doesn't necessarily act properly discontinuously, but here it's acting by isometries. And what's crucial here for PSL2R is that the stabilizer of a point is finite. Okay, so this is something you already know. These are elliptic elements, which so if there's some element here that fixes a point, then it has a finite order. Okay, so this is some basic fact you know. So that's used in the proof of this. You have to that fact about PSL2R needs to be used. So it uses this PSL2R has finite sort of stabilizers of points. Okay, so. But otherwise, this is something easy to prove. You can show that discreteness means that your orbits are spread apart. Okay, so as a consequence of this, so as a corollary, you have that if you start with a discrete faithful representation, then you can take quotients. Okay, so if something acts properly discontinuously, so let's say gamma is the image group, then this quotient of H2 with gamma makes sense. It's a nice enough space. If it acts properly discontinuously, it's Hausdorff, for instance. But this is also is a hyperbolic surface. Okay. Why is it a surface? Well, it also, this action, since it's faithful, this action is also free. Because if it's faithful, then you know that the image group is pi1 of S, which has no torsion. It's a torsion-free subgroup. And so it can't fix an element in H2. Okay, so anything that fixes an element in H2 is finite order. Okay, so, and of course, it acts by isometry, so the metric descends in the quotient, you get a hyperbolic surface. So that's the connection with hyperbolic surfaces. And in fact, let me also say that moreover, if S is a closed surface, if you started out to be a closed surface, it's a fundamental group of a closed surface, then this quotient surface is homeomorphic to S. Okay, so the quotient surface better have fundamental group also pi1 of S, because we're looking at it. And then there's only one surface, if you're looking at closed surface, there's only one surface with that fundamental group. And so, you know what surface you get if you start with a closed surface. Okay. If it's not closed, then it depends on this number of. So it's always a free group, but you don't know whether the genus contributes to the generators of the boundary. Okay, so all right. So let me give you some examples, some pictures. So these discrete subgroups that act nicely and give you good, nice quotients are what are called Fuchsian groups. So, yes. Right, yeah, maybe there's some argument like that. Yeah, so, the key thing is that you have a discrete, and if you have a discrete group that fixes a point, then that element needs to be finite order. Okay, so you only have finite order elements that fix it. Yeah, otherwise, yes, you can have rotations that fix the point. Yeah, so maybe I should not have, so let's see. I'll just replace this. Okay, so if you have a discrete group, then I'll find it. All right, thanks. Yeah. Okay. Okay, so let's look at some examples of discrete groups. So the first example is, suppose you have some group gamma, which is generated by a hyperbolic element. Okay, so that's an infinite cyclic group. So lambda is some positive number here. So what does its action look like on the hyperbolic plane? Well, so the action is the dilation, is lambda squared z. So it looks something like this. So you have, so everything sort of dilates, it pushes outwards. There's a geodesic axis, there's an axis here, and the fundamental domain looks something like this. There's some between two geodesics. And the quotient, so that's our upper half plane, and this group acting here. And the quotient obtained by taking a fundamental domain, and takes this side to that. So when you glue them, you get some annulus, hyperbolic annulus that flares out. Okay, so as you go here, the distances increase. So that's our H2 mod gamma, and this central geodesic axis is this part defines a simple closed curve in the core of this annulus, and this has, you can also, so this closed geodesic, you can compute its length. It's 2 times log of lambda. Okay, so if this is, let's say I, this is lambda squared I, you know from formula of hyperbolic distance, you can find out its length. Okay, so this kind of, so on one side I'll call this a funnel. Okay, so this kind of flaring end. Okay, so that's a funnel. So that's a picture of a discrete group. Here it's very simple, it's just an infinite cyclic group. You can also look at an infinite cyclic group generated by a parabolic element. This is again some discrete group. This time it acts on the H2 by translation. Okay, so here you have fundamental domain, which is this vertical sort of strip, and this element acts by a translation by 1. So this group generated would have this fundamental domain, which let's say one of these central guys. So that's the picture in H2. You get the styling by these strips. And if you look at the quotient, then, well, you get something like this, which narrows down. As you know, the distances across decrease as you go up. And so you get what is called a cusp. Again, it's topologically anomalous. You can get more interesting surfaces of discrete groups. I think we're interested in surfaces anyway. So one example of this is, suppose I look at H2. Now I'm looking at the disk model, the Poincaré disk model, and suppose I have two hyperbolic elements that act by translating sort of. So it's a hyperbolic element. I'm not drawing the axis is somewhere here, but it translates and takes this geodesic to that geodesic. So, and then there's another hyperbolic element that takes this geodesic to that. So if you look at gamma generated by A and B, so these are the hyperbolic elements as shown in the picture, then you would get a discrete group, it turns out, and it generates a tiling of the hyperbolic plane. Okay, there's some kind of tiling by these quadrilaterals, and it's a free group. Okay, there are no other relations. Okay, so gamma acting this, and the fundamental domain is this central, this quadrilateral I started with. So what you get as a quotient is going to be, so it's your identifying sides of a square, except that one point is at infinity, and you get a hyperbolic once-punctured torus. Okay, so and there is a cusp at the end, and you can, if you sit down with this, you'll figure out that this commutator is actually an element that is parabolic. Okay, and the picture there looks like this second example. Okay, so that's another example of a discrete action and the quotient giving a hyperbolic surface. And you've already seen examples which give you compact surfaces. So if you start with on the hyperbolic plane, if you start with some octagon, which is regular, and all sides are. So let's see, 1, 2, 3, 4. Okay, so I hope I have 8 sides, and you identify alternating sides by some. Okay, maybe there's one more side missing. Okay, so you identify sides by isometries, A, B, A prime, B prime. So that's a hyperbolic octagon, which would mean that they have geodesic sides, and with all interior angles pi by 4. So this, you know that such things exist. And if you look at gamma generated by these hyperbolic translations, okay, so A, B, A prime, B prime, then it turns out that this is isomorphic to the fundamental group of a closed surface of genus 2. Okay, so the relation is automatically satisfied. Okay, so if your picture is like that, so A, B, commutator, the product of the commutators is the identity. So, and as a quotient, and this generates a tiling, which I won't try to draw, okay, of the upper half plane of the disk model. And the quotient of the hyperbolic plane with this action gives you a genus 2 surface. Okay, so this is something maybe you've already seen and already familiar with. Okay, so that's a compact sort of hyperbolic surface you obtain as a quotient here. Okay, and this is again a discrete group that generates this tiling. So here is one example of when we started with the fundamental group of a closed surface. We get back the closed surface here, but for free groups, you can have other examples. So this was one example where the group was a free group on 2 generators. Here's another example where a free group on 2 generators gives you a different surface as a quotient. So if you start with A and B that take geodesics that have disjoint axis, and once again, it has a translation. It takes, let's say, this geodesic to this, and this to that. Okay, so then this group generated by A and B, as shown, is also a discrete group. It's also a free group. Okay, and you have, so some kind of picture generated by iterating, sort of looking at the orbit of this group, and the fundamental domain is maybe the central guy. And as a quotient this time, so that's our picture here, and as a quotient you get so you get something which looks like this. It's going to be a pair of pans secretly, but you have these funnels attached to it, so that it becomes a complete surface. It's some kind of completion of a hyperbolic pair of pans. And you can, if you inspect this picture closely, you can probably see some of these hexagons hiding over here. So maybe so the picture looks like this. There are these. If you look at these perpendicular, these shortest arcs, these geodesics between them, these are, let's say, these are the axes of A and B, then you would see 2 hexagons in the picture. Okay? And then there are these ends adjacent to these. So these give you these funnels. Okay, so it's sort of, you're adding funnels to so these geodesic boundary components to complete it. Okay, so this is sort of the picture you get when your fundamental group is, when gamma is generated by these 2 elements. Okay, so when you are a free group in 2 generators, you don't know which surface you'll end up in, but for a closed surface, if gamma is isomorphic to the fundamental group of closed surface, then you do know that you get back the closed surface. Okay, so so I just stated it. You can, so there's some condition on when you would expect, let's say you're given 2 matrices, A and B. How do you know whether the group generated by it is discrete or not? Okay, so in this case, for example, you would require, for this picture to work, you would require that these A and B, these have hyperbolic elements with disjoint axis. Okay, that's one thing. But you also require that there's some relation between, they should be sufficiently far apart. Okay? And in fact, since I've mentioned the color function, so it is a fact that if you look at, so let's see, so the distance between the axis of A and B should be greater than the color functions of the translation length. So let's say the length of A, by this I mean the translation length of A plus the color function, the translation length of B. Okay, so I think this is the sort of the criteria that so you can check, but it's not always going to work. And I kind of just indicated this as sort of the kind of examples that arise. Okay, but okay. All right. So yeah. So let me make two remarks about this. So first of all, you don't just get a hyperbolic surface, but you also get a marking in this process. Okay, so remarks. So one is the quotient surface acquires a marking. Okay, so how do you see it? Well, okay, so walk all the way back here. So let's see. So here, so what you do is here. So you look at the generators of the fundamental group. Here, it's just one element, and look at its axis. This axis, the group acts by translation along this axis, and the quotient you get a closed geodesic on the quotient surface. Okay, so that gives you a curve in the surface, and that happens in all these cases. Here, these axes, which I haven't drawn, but they're axes for A and B. And the quotient surface, they give you closed geodesics corresponding to A and B. And these generate this gamma, generate the fundamental group. Okay, so, and here, of course, you've seen these pictures. So if you look at axes of A and B, you get so an axis of a hyperbolic element is this unique geodesic that is left invariant, and that's right. Yes. Okay. So, so things which look like this. Okay. So it's conjugate to is like this. So here, 0 and infinity are fixed. So that's a hyperbolic element. That's right. Yes. Yeah. Okay, so the way that you get the marking, so remember that all you need is one curve for each of these generators of the fundamental group. So if for any generator alpha of pi 1 of s, consider the geodesic axis of rho of gamma, a rho of alpha in H2. So we rho of alpha is a hyperbolic element, and you look at its geodesic axis, and this descends to the quotient surface to H2 mod gamma as a simple closed geodesic. Okay, so let me say it's a closed geodesic, and once you know these image curves, okay, on the quotient surface, which corresponding to each generator of the fundamental group, then that's equivalent to telling, giving you a marking, right? So that's what we discussed the last time. Okay, so it determines a homeomorphism up to homotopy from a fixed surface to our given hyperbolic surface. Okay, so that's number one. Number two is that if you conjugate your gamma, so conjugating gamma gives you, doesn't change the hyperbolic quotient, right? It gives an isometric quotient. Okay, so surface. Okay, so if you replace gamma with gamma A inverse, where A is something in PSL2R, then let's call this gamma prime, then H2 mod gamma and H2 mod gamma prime, they're isometric. Okay, so, how do you see this isometry? Well, you can look at, so the whole picture then sort of shifts by this isometry A, so it's a map from H2 to H2 multiplies by A or A inverse. I'm just, you have to check, sort of passes, so this sort of some kind of square like this commutes, and this is an isometry, and this induces an isometry from between the quotients. Okay, so it's easy to see that if you conjugate your representations, or the image groups, for instance, then the quotients will not change. So that's why in our representation variety, we were quotienting by this action of conjugation. Okay, so an upshot of all this is sort of a, let me just give this kind of a summary. So we have, from what we discussed, the following proposition that if you start with so any representation which is discrete and faithful in this representation variety determines a point in the Teichmuller space of S, like a marked hyperbolic surface here. So I'm assuming that, let's say, S is closed. Okay, so because so that you know that you get this surface and take a quotient. So this is the sort of the summary of what we discussed. Okay, so but what we really want is the other way around. So I want to tell you, given a point in Teichmuller space, how do you get something which is in the representation variety? In fact, you get something which is discrete and faithful. So what is this map? So if you start with a marked hyperbolic surface, so what representation, how can you build a representation from the fundamental group to PSL2R? So I need to tell you this, okay, and this will sort of complete the picture. So this, the answer to this, and that will be the next half of the. So this row is what is called the Holonamy representation. Okay, so some of you already know that there is such a discrete group acting on H2. It gives this surface as a quotient because you know this universal cover is isometric to H2, and the tech translations of the fundamental group act on that. But I'll try to embed it in a slightly more general discussion of Holonamy representations of geometric structures. Okay, so the thing to note is that a hyperbolic metric on S, as we had sort of talked about last time, is also a geometric structure. It's a geometric structure modeled on PSL2R as a group and H2 as some model space. Okay, so in other words, you can think of a hyperbolic metric as on the surface S, you have charts to the hyperbolic plane. So locally, it looks like pieces of the hyperbolic plane. And on the overlap, so suppose you have phi1, phi2, two charts. There's phi2, phi1 inverse defined on the overlap. The overlap, they are elements of PSL2R. Okay, so this belongs to PSL2R. So there are charts to H2 and transition maps defined on the restrictions of elements in PSL2R. So that's what a hyperbolic metric really is. It's a geometric structure. And this belongs to a more general notion of GX structures. Okay, so more generally, so if you take G to be some Lie group and X to be some homogeneous space on which this group acts nicely, then you can talk of a GX structure just like you did here. This time you would have charts to this homogeneous space, and transition maps would be restrictions elements in this Lie group. Okay, so this everything else now say in the next few minutes will be part of this more general discussion. So if you have such a geometric structure, let's say a hyperbolic structure, then so this is sort of the local description. So you have charts to locally, you have these charts to H2, but you can extract from it a more global description of the structure, which is equivalent to our local description. And this is in terms of what is called the developing map, which is a map from the universal cover to H2, our model space, and a Holonamy representation. This is what is going to, define the representation for us. Okay, so let me. So this is a representation fundamental group to PSL2R. Okay, so let me try to describe what these are. So the developing map is obtained. So here's the universal cover. So what you want to do is you want to define, instead of these local charts to H2, you want to define something globally, a map from the surface to H2. And you can't quite do it on the surface, but in the universal cover, you can start to define a map. So let's say you fix a base point, and you want to define a map to H2. So you start with a base point and an initial chart. So fix a base point x0 and an initial chart, let's say phi naught, u0 to H2. So there's some open set. You know that so on the surface you have charts to H2. That so it's in the universal cover you can do the same, and so you have some kind of so on this u0 you can define a chart to H2. Okay, so you at least you can start with this. Okay, and we want to sort of build a map on the entire universal cover. How do you do it? Well, you sort of analytically continue. So suppose you have a path in the universal cover. So let a gamma tilde be a path in the universal cover. So then you want to define the developing map on the end point of the path. So remember that sort of the universal cover. So the points here you can think of as homotopy classes of paths. So there's a unique, simply connected, so there's a unique homotopy class of a path from x0 to that point. So you want to be able to analytically continue this developing map along this arc, so you can define it at the endpoint. So you cover gamma naught by charts u0, u1 up to un, which form some kind of chain like this. Okay, so there's some bunch of things reaching, let's say, un, which covers the endpoint. And for each, you can sort of, and we define, you extend this definition of developing map. So initially you start with the developing map on u0 to equal this initial chart, and we define the developing map on the union of these charts inductively as follows. So what's going to be the developing map on the next chart? So the next chart u1 might be mapping somewhere else on the hyperbolic plane, but you know that there is an element of PSL2R that brings this back so that it matches. Okay, so this is the transition map. Okay, so T1. So let's call it T1. So this developing map on U1 can be defined to be this chart phi1 followed by T1, so that you now this defines. So this together with our map already defined, they match. Okay, so now you have something defined on U0 union U1, and you continue. Okay, so developing map on U2 there's another chart that brings it back like this, and so on. So you can patch together these charts by post-composing with these elements of PSL2R that bring you back so that the maps match with what has already been defined. Okay, so this is how you can inductively define the developing map on this union of these charts. And in particular, this includes when you finally get to UN, it includes this endpoint as well. Okay, so you've defined developing map on the, let's say, the entire path and including the endpoint. And you can check that this doesn't depend on the homotopy class of the path. So if you can keep the endpoints fixed and you homotope the path, I mean, if you homotope it a little bit, you already see that you don't need to change the charts anyway. Okay, so this indeed defines a map from the universal cover to H2. That's a globally defined map. Okay, and so you can think of it as some kind of unwrapping the hyperbolic structure, this geometric structure on the surface. So you can't quite do this process on a surface, because if you look at a loop, you come back, and if you try to define some global map, and you kind of piece together these charts, analytically continue, when you come back, there might be a difference of these two charts by some isometry, some element of PSL2R, and you don't want that, but so you have to pass through the universal cover. And the Holonamy representation is somehow it's recording that mismatch for loops on the surface. So it's instructions for how to wrap up. So this is an unwrapping. And so how do you define that? So it's a representation by 1 of S to PSL2R. For any loop, it assigns this to this loop this composition. Okay, so where for this composition for the path for the lift gamma tilde passing through, or sort of starting from the base point. Okay, so this it turns out this is it's a homomorphism. So if you concatenate paths, and if you take gamma and gamma prime, you have to start the process all over again from this endpoint. And so this whole so this composition is sort of preceded by the previous isometry. So you indeed compose in the correct way. So this row is a representation. It's a homomorphism. Okay, and by definition, so since we have this, there's some kind of so there's a compatibility between these two. So you notice that what happens is this developing map for any x in H2, gamma and pi 1 of S. The developing map and representation are intertwined this way. This is developing map is equivariant with respect to this pi 1 of S action on the universal cover, and this action by the image of the representation, the group gamma. Okay, so here's the universal cover. You know that the fundamental group of the surface acts on the universal cover. The developing map transports this action to action on H2, but the gamma. But the gamma is this, as usual, is the image of this representation. Okay, so you have this kind of equivariance as well. Yeah, so you have to fix this. That's a good question. So you have to fix this base point and this initial chart to start the process of defining. So this was a choice. So what happens when you pick another one? So that's let me come to that. So let me note. So this whole construction depended on that choice of this initial chart. So number one is so if you change the initial chart, let's say you replace phi naught with phi naught composed with A, where A is some isometry of the hyperbolic plane. You're just moving it somewhere else. Okay, so then it turns out the developing map just gets pushed by the same isometry. You get a different developing map, and the Holonamy, this representation, gets conjugated. Okay, so perhaps it's something like this. Okay, so it's either this or that. So changing that initial chart just conjugates the representation, and And this is why, once again, I mean, so in the representation variety, we have to quotient with conjugation. So it's well defined as in that quotient space. Okay, so in that representation variety, you get a well-defined holonomy representation. So that's so one consequence of a construction. There's another thing to note is here is that we have, in all that we said, we have implicitly used a marking on our hyperbolic surface. Where have we used it? Well, so remember that I told you that to define this holonomy representation, we take a gamma, that's some element of pi 1 of s, and then we said that, okay, let's lift this gamma tilde. So that means that we already know what gamma looks like on the hyperbolic surface. Okay, so we've implicitly used an identification. We know what curve on the surface gamma is. So gamma is something in the fundamental group, and so that's being thrown onto this hyperbolic surface. So we've kind of implicitly used the fact that we started with not just a hyperbolic surface or hyperbolic metric and stuff, but also a marking. Okay, so we needed that. And the third thing to note is actually a lemma, and I won't go into the proof of that, is that if the hyperbolic metric is complete, okay, so this means just metrically complete, or as complete as a metric. So then the developing map is a diffeomorphism. So this is a completeness automatic when your hyperbolic surface is compact. Okay, so then it's automatically complete. Yeah. So why is this true? Well, it turns out that so if you are complete. So first of all, developing map is by construction a local diffeomorphism. Okay, so locally you're sort of building it by charts to H2. So if you have a local diffeomorphism, if it's also complete, you can actually check that the path lifting property holds. Okay, so somehow, so we kind of did the sort of the other way around, but so it's not hard to check that if something is complete, if you can lift paths on this. Yeah, so from the from H2 to here. Okay, so you can continue paths. And once you have that something is local diffeomorphism and has the path lifting property, it turns out it's a covering map. Okay, so and what covering map can you have to a simply connected space? Well, it has to be a diffeomorphism. Okay, so so this is a fact, and this is how in this picture you now can identify the universal cover with H2. Okay, this is the way that this identification works. You can kind of, you already knew by Carta-Hadamard theorem that Harish talked about, or something, that the universal cover is H2, but this is one way of sort of elaborating on that fact. Okay, so yeah, we've used a marking here, right? So when we kind of yeah, so this works. So for a marked, we have kind of assumed that you have a marked surface. So this, so we have identified the surface. So if you replace pi 1 of s by pi 1 of x, where x is the hyperbolic surface, then it's fine. But here we have fixed an s, which is sort of abstract. We fixed it before. Okay, and we're starting with a hyperbolic surface which is homeomorphic to it. Okay, so when we talk of an element of pi 1 of s, we don't quite know what it looks like on the hyperbolic surface. So that requires a marking. Okay, so yeah, otherwise, I mean, if you don't like markings, then you can sort of forget about this s and just keep this as x, okay, our hyperbolic surface. And then indeed, yes, for every generator on the hyperbolic surface, you have this holonomy representation. But we want a representation not from a pi1 of our hyperbolic surface, but from a fixed surface that we've kind of chosen, sort of a prime. Okay, so that's, yeah.
The developing map restricted to U1 is T1 compose phi.
Yeah.
Phi 1, right?
Yeah.
So you apply phi 1 on U1 to H2 and then apply T1 on that to come back to U0, right?
Yeah. So this is to bring this piece back so that it defines something, continuously extends. Yeah.
Define the next map.
So did I get this wrong? So maybe this is T2. Yeah. That's right. Yeah. So it's an inductive process. Okay. Maybe I wrote it. So you have phi 2.
Then T2.
Yes.
And then T1.
Aha. Okay. Is that correct now? I see. So here you have. So then I got the order wrong. Is it?
Yeah.
All right. So but we really want this. So let's just note this. I mean, so a corollary, let's say a corollary of all this is the fact that the holonomy representation of a complete hyperbolic structure metric is discrete and faithful. Okay, so coming back to our discrete and faithful representations, and the proof of this now is, well, if suppose it's not faithful, suppose if this representation can take something to the identity where gamma is some non-trivial element of pi1 of S. Okay, so suppose you have that. Okay, so then, well, you know that this developing map is equivariant with respect to this pi1 S action. So you have this. So we know this, and this implies, so this is identity, so implies that the developing map takes the gamma acting on X, and it's the same point to the same point as it takes X. But developing map is a diffeomorphism, right? So you know that gamma must be fixing that point, and the gamma must be identity since pi1S action is free. Okay, so that's what happens when so this is why it's not it has to be faithful, and similarly, so if it's not discrete, then you have some sequence of elements which converge to the identity. So then, I mean, using that same relation between developing map and the holonomy representation that we have, we get this. But this implies that, again, since the developing map is a diffeomorphism, this amounts to saying that this orbit has an accumulation point. Okay, so and that cannot be also because pi1 of S action on the universal cover is properly discontinuous. Okay, so contradicts pi1 of S action on S tilde is properly discontinuous. So, in other words, this developing map really sort of transports this action pi1 S on the universal cover here to this action of gamma over here, and so the gamma must be acting properly discontinuously freely, just like pi1 S. So you indeed get a discrete and faithful representation. So a consequence of all this, so to summarize, so we now have defined, we have this map from Teichmuller space to a space of this discrete faithful representations. So we now have that the holonomy representation. The holonomy, let's call it map, hol from Teichmuller space to discrete faithful representations of pi1 of S to PSL2R. So this is now well defined. So you take a marked hyperbolic surface to a representation, which is the holonomy representation. And it lands in the discrete faithful part. And from what we've discussed, it's so this map is not only well defined, it's actually injective. After all, if you get the same the representation determines the hyperbolic surface again. So this is like the previous proposition that we got. So you quotient with that image group, and you get back that hyperbolic surface. So it's injective, and so let me also add, it is also continuous. Okay, so the continuity part, so I won't go into details of that, but let me give some kind of hint. So, so why is it continuous? Why is this assignment of a holonomy representation to a Teichmuller space to a marked hyperbolic structure continuous? So okay, so I am also out of time. So so the reason is, firstly, I mean, so you know that the topology on Teichmuller space is given essentially by the fact that length functions are continuous. So here on the representation variety, it turns out that that trace functions give coordinates to the representation variety. And what are these trace functions? Well, for any curve, for gamma, a simple closed curve, you can define a trace function gamma that takes a representation and it looks at the trace of the matrix you get by when you look at rho of gamma. Okay, so these define functions on the representation variety, and it's well defined because these are invariant under conjugation. The trace is invariant under conjugation, and it is a fact that these trace functions give coordinates, and these traces are. So that's fact one, and fact two is that these traces are related to the lengths of curves on the original surface. So this so remember that when you started with a single hyperbolic element, lambda 0, lambda inverse, we knew that get a closed geodesic of a certain length. And so the trace and the lengths have a relation, and I don't quite remember what it is, but I think it's something like trace squared of rho of gamma is perhaps 4 square of the, something like this. Okay, so let me just check this. Okay, so it's a trace and hyperbolic length of a geodesic are related. Okay, and so if you move continuously, if you vary continuously in Teichmuller space, all the lengths of curves would be varying continuously, and in the image if you measure their traces, then they will also vary continuously. So you can, in fact, check that so this is continuous. And for S closed, so the previous proposition tells you that this is a homeomorphism. Okay, so it's also surjective because the representations for every discrete faithful representation, the previous proposition we got a marked hyperbolic surface out of it just by taking a quotient. So indeed, this is a continuous bijection, and we already know that U of S is a cell. So it tells you kind of more. It tells you that it sits inside. So it is an open map. Okay. So all right. So I didn't get time to say, but let me just say it again. So also the fact is that this space of, so if S is closed, this representation It's discrete faithful representations. So this is a closed surface. Then this discrete faithful representations that you get as an image here, the image of the Holonamy, is a component of the representation variety. Okay, so let me just say it's both open and closed. Okay, and yeah, so openness is again, is a part of a more general fact. So let me just give some. So openness, I mean, in this context, originally it's a theorem of André Weil. So here you can, if you've already kind of seen this, so this is a homeomorphism to its image. Okay, so as you explain, this is an open ball, and you image something which is open, and closeness is a theorem of Chakro. Okay, so in any case, this forms a nice subset of the representation variety, and which you identify with Teichmuller space. So this is another way of thinking about Teichmuller space. Okay, so, all right, I'll stop here.